Welcome to the 28th lecture for the NPTEL course on computer system optimization for machine learning. Today we will continue discussing on KV cache and then we will start discussing on paged attention. So as we discussed in the last lecture, since we are decoding, all these LLMs are all these LLM work in autoregressive manner. That means each time we decode one token and that token is appended to the sequence, the whole sequence goes to the decoder and so on and so forth, right. So in the last lecture we saw that there are some redundant computation and then we don't need to do those computations in while generating every token. So we can save those values, we can save those key and value pairs so that we can reuse them in the subsequent token generation. So that's the KV cache, right. Again, as I already told you, KV cache is not a separate physical cache in the computer. It's a general misconception. It's another set of memory, or it's another set of data which needs to be stored. So since this data is stored, it is known as cache. But in reality, this data, this KV cache is actually stored in the main memory. Okay. We will soon see that the KV cache size is very big. So there is no way that we can actually fit the entire KV cache in some physical, let's say L1, L2 or L3 cache. Okay. Now let's see how big can this KV cache be. Okay. So what we will do is we will take one representative transformer model or representative LLM and then we will compute the amount of memory or amount of storage required for this KV cache. Okay. So let's assume that we have n layers, which is the number of layers in the model. D model is the dimension of the embeddings. Sequence length is the length of context in tokens. Okay. When we say length of context in the tokens, that means how many ever tokens have been generated so far. Okay. Or if it is decoder only model, so we can think that how many ever tokens are there in the prefill. Okay. Now let's also assume okay, so with these parameters we need to know the size of the KV matrices or size of the KV cache. Now so D model, if you remember, all the matrix size of the QK or all the matrix size of K and V were all the matrices of K and V were of the size of D model by sequence length, right. That's what the matrix size is. So that means we need to store these many numbers, D model by T model multiplied by sequence length, and since we have key and value, we have two variables, so we need to store this 2 multiplied by D model multiplied by sequence length, these many numbers. Okay. Now let's say when we talk about memory, we need to know what's the precision of the numbers, right. If we need to know that how much memory some numbers will take, we need to know what's the precision of the number. So let's say when we say precision, that means we need to know the bytes per number or bytes per parameter. If we have FP32, if the precision is FP32, then 1 byte is 8 bits, so we will have total 4 bytes, right. So that has to be multiplied with the total number of parameters, like 2 multiplied by D model multiplied by sequence length is the total number of parameters we have to store. That has to be multiplied by the precision, right. Now remember, we don't have just one layer in the large language model or in the transformer algorithm, right. So we have total n layers, right. So that means this whole expression or this whole amount of bytes has to be stored for each layer, and then the total number of if the total number of layers is n layer, then the total number of bytes or total memory requirement will be this expression multiplied by n layers, right. So that's the size of KV matrices, right. Hopefully we understood this. Now let's see, now let's take some real numbers. Okay, let's take some real numbers and then see that how much actual memory the KV matrices take, right. So let's say we need to know what's the maximum batch size a Llama 2 7 billion model can fit on a A100 GPU, right. So that means when we need to know this maximum batch size, that means we need to know how many of those KV cache will be fitting on the A100 GPU memory. Okay. Now remember, on the GPU memory we have to store the KV cache, yes, but before that we have to store all the weights on the GPU memory, correct. So when we say 7 billion, llama 2 7 billion, that means it has that many number of parameters or that many number of weights. Okay. Now let us say these are the parameters of the GPU as well as the large language model. Let us say the GPU has 80 GB of memory. We already have seen that llama 2 has this 7 billion parameters. When we say llama 2 has 7 billion parameters, that means it has that many number of weights. Okay. Now let us assume that we are talking about 16-bit floating point numbers for all activations and weights. That means the precision is AP16. Llama 2 has 32 layers. Let us also assume that the D model, the embedding size is 4096 and sequence length is also 4096. Okay. Now the model parameters, if we talk about the model parameters, it will take, when we say model parameters, that means we are talking about the amount of weights or the number of weights, right. So the weights will take some storage or some space in the memory, and that space is nothing but bytes per parameter multiplied by number of parameters. So since we are talking about AP16 precision for all weights and activations, that means 16-bit number for all weights and activations, that means for all weights and activations we will have 2 bytes, correct. Now since we have 7 billion parameters, we will have total 14 billion bytes, that means that is nothing but 14 gigabyte. So this 14 gigabyte is required for storing the weights of llama 2 7 billion parameter model. Okay. Now we need to calculate, so we cannot store, we cannot store anything, we cannot use all 80 GB of GPU memory for KV cache. Okay. Some amount of the KV or some amount of the GPU memory has to be reserved for the weights. Okay. Now the amount of remaining memory is 66 GB, right? 80 minus 14 GB is 66 GB. So now we have to see what's the requirement of KV cache, or how much GB of memory the KV cache of this llama 2 7 billion parameter model needs for one batch, right. So again we already saw that KV cache per request is when we say one batch, that means we are assuming that the batch size is 1. Okay. Here we are assuming that batch size of 1. So that means in one batch there are only one request. Okay. So we already have seen that KV cache per request can be expressed as 2 multiplied by precision multiplied by number of layers multiplied by D model multiplied by sequence length. Okay. Now with that, let us compute how much memory each request, or how much memory the KV cache of each request needs. So that will be nothing but 2 multiplied by 2. So precision is AP16, that means it will require 2 byte, number of layer is 32, D model is 4096, the embedding size is 4096, sequence maximum sequence length is 4096. So if you just multiply, you will see that we need 2 GB of memory per request, or 2 GB of memory for KV cache per request. Okay. Now we have now we need to calculate the maximum batch size, right. So remember, we have 80 GB of memory for the GPU, and then 14 GB is already required for the model parameter, correct. That is the required memory size for the model parameter, and if we divide it by the KV cache per request, that will give us the maximum batches. Okay. So that will give us 33, right. Now one very important thing to note here is, see, it is a 100 GPU, it is a state of the art GPU with 80 GB of memory. 80 GB is lot, right. Now that state of the art GPU with like huge amount of memory can only sustain 33 requests. Why? Not because GPU does not have enough compute, but because GPU does not have enough memory. So again, we can always think that all these machine learning models are probably compute bound, it needs huge compute, but no, actually we need more and more memory. Okay, so I mean, in this state of the art GPU with this high amount of memory, you can only sustain this 33 number of batches or 33 requests. That's pretty low, right? I mean, we would have thought that, I mean, these GPUs has very high amount of compute and memory, probably it can sustain thousands of requests at the same time, but no, each of the requests generates so huge amount of memory, or it requests so huge amount of memory space that the GPU can sustain only 33 requests. Okay, and that's a low, that number is very low. Now again, another catch here is we just assumed that all the KV cache, or the entire KV cache for all the requests can be packed in this 33 GB, in this 66 GB of memory, right? So we just told that 14 GB is required by the weights, and remaining 66 GB is available for the KV cache, and we also assume that we can actually pack all the 33 requests, or the KV cache of all the 33 requests in that 66 GB. That is also not true. I mean, we cannot pack that dense. Okay, we will soon see why, but this 33 or this type of calculation is also kind of overestimation. This is probably back of the envelope calculation, but this is an overestimation. So as you can see that it's not easy to sustain multiple requests or to sustain very high number of requests on the GPU during the inference. Okay. Now with that, let's go to the next topic, which is paged attention. Okay. Now we already saw that the KV cache requires lot of memory in the GPU. Now let's try to see why we need to manage the memory, why we need KV cache memory management. So whenever we have, whenever we use all these agentic AI tool, there are different number of or different types of input, and different types of input has different types of memory footprint or different types of execution. So the first type of input is, the first type of request is long input, short output. Okay. So that means the input will be long, whatever we are putting on the prompt is long, but whatever output is generated is short. Okay. So the use case is summarization, meeting recap. So I mean, many of you have probably noticed that nowadays in Teams meeting, Copilot is integrated, right? So I mean, the whole meeting is kind of like 1 hour or maybe even longer than that, and then the Copilot takes the whole meeting and then generates summary. So that's a short output. Now in that case, the memory on the GPU will be occupied by the model weight. Then prefill will have a good amount of memory, because, or prefill will require a good amount of memory because our input is long, right? And then decode will have decode will occupy relatively short amount of, or relatively small amount of memory, because our output is short, right? So that's the use case. Summarization, meeting recap, etc. are the use case of long input, short output. Then we have long input, long output. So again, that is one example of long input, long output is rewrite or edit documents. So let's say you are asked to write an essay, you wrote it, but then you want to polish it, right? Or you want to correct the grammar, etc. Correct. So in that case, you will put the whole essay as the prefill, and then I mean, as decoded tokens, you will get similar amount of similar number of words which you put in the input, right? So that's a long input, long output sequence, or long input, long output type of request. So there also you can see that prefill amount of memory required for the prefill is probably similar to, or is as large as the amount of memory required for the decode. Again, I mean, pay attention to the type of figure we have. So we have a big chunk of memory for the prefill, but then we have smaller chunks of memory for the decode, right? Because remember, whenever we are decoding, the tokens are generated in an autoregressive manner. So that's why, I mean, one token at a time, we are generating one token at a time. So right, so the memory requirement will be increased like sequentially. Then we have short input, long output. That is one example of short input, long output is writing an essay. So if you just ask that write an essay about probably Indian Institute of Science, then the input is short, but the output will be long, right? So that's why you can see the amount of memory required by the prefill is less, but the amount of memory required by the decode or the generation of the token will be more, right? And then the finally we have short input, short output. This is one example is the short question and answer or the chat bots, right? Whenever you buy something from many of those shopping platform like Amazon, and then probably you are not happy with the product, then you just go to the chat box and then say, I mean, like, hey, I want a refund, right? Then probably the first response you get is thank you for buying product from Amazon, something like that. So that's a short question and answer type of request, right? So for that, both prefill and the decode will require a smaller amount of memory in the GPU, right? But in all these cases, this model weights will require equal amount of memory, right? Now, as you can see that different types of request will need different types of or different amount of memory for prefill as well as decode, and that motivates why we need to do KV cache memory management, right? So, I mean, that's the observation, different input requests require different amount of KV cache, right? Now, another observation is tensor computation needs contiguous memory allocation. So, for an example, I mean, if you know about memory management in OS, you will understand that we always need contiguous memory allocation in the memory space. The addresses where all the data is stored, they need to be stored in a contiguous memory allocation. So earlier system like faster transformer allocate maximum model length of KV cache for each request. So let's say in the previous example, we saw that each request will take maximum of 2 GB of KV cache, right? So this type of technique, faster transformer type of technique, will just pre-allocate that much of memory, right? So let's say we have two prompt. Prompt one was how was your, and prompt 2 is help me write a, and in both cases let's say maximum model length is 10. So the earlier system will just allocate the memory required for this 10 tokens, or the KV cache memory required for 10 tokens in the memory. So let's say this was our prompt, how was your, and then another prompt was help me write a. For both the cases 10 slots will be reserved, right? But then it might be the case that the first request was how was your day, the request was how was your, but let's say the decoded token is day and then end of sequence, okay? And then for the second prompt, the input was help me write a, and then let's say the decoded token is poem and then end of sentence, right? So in this case, but then remember we already reserved 10 slots for both these requests. Of course, we don't need all these 10 slots, but why did we reserve 10 slots? Because the maximum model length is 10, okay? Now then that means we have some wasted space, correct? As you can see that in this case 1, 2, 3, 4, 5 slots, and then in this case 4 slots are wasted, correct? So that is called internal fragmentation. If we perform this fixed pre-allocation, that results in internal fragmentation. I mean, this part of the memory cannot be used by any other request or any other the KV cache of any other request. So this is called internal fragmentation. And then let's say we somehow identify that how was your this particular prompt requires less number of tokens. So although the maximum model length is 10, maybe we say that the maximum token is 8, the number of maximum tokens will be 8, and then for this particular prompt help me write a, the maximum model length is 10, and then let's say we also say the maximum number of token is 10, right. Now still we will have this internal fragmentation, because in this in prompt 1 we have 2 tokens generated. So that means we need to store the KV cache of maximum 5 tokens. That means still we have these 3 slots wasted. So that is the result of internal fragmentation, right. Now there is something called external fragmentation also. So what happens? So usually, I mean, probably that this problem of external fragmentation might not be there in newer OS or newer GPUs, but let me first explain what is external fragmentation. So usually what happens, I mean, there are buddy allocators which allocate memory. Okay. Now typically the memory allocation has to happen in the power of 2. Okay, the amount of memory allocated has to happen in the power of 2. So it might happen that due to the fact that the memory allocation is happening in the power of 2, some amount of memory is getting wasted. I mean, some amount of memory is not getting allocated at all. So that is called external fragmentation. So in this case, these 2 slots were not reserved, or these 2 slots were not allocated due to external fragmentation. Okay. Now so that's the fourth observation, that external fragmentation is caused by these buddy allocators. Now of course, one way to get rid of this problem of external and internal fragmentation is, what if we could predict the decode length exactly. So given the prompt, whenever we receive a prompt, what if we have a mechanism that we can predict the exact decode length. I mean, you give a prompt and then we can say that, okay, with this prompt we will have 20 tokens in the decoding phase. That is good, but will that solve external internal fragmentation? Yes, but will there be any other problem? Of course yes, otherwise this lecture would have been ended. That is not perfect, that is also not perfect. So let us take one example. Let us say again we have let us say 2 prompt 1 was prompt 1 is how was, and the second prompt is help me write a, and then it generated 2 decoded tokens, one is poem, another is end of sentence. Now let us say okay, so let us say in the first prompt we have allocated this much of memory. I mean, when we say we allocated this much of memory, assume that somehow we predicted that the decode length will be 8. Okay. So 2 tokens were there in the prefill, and then let us say we predicted that 6 more tokens will be there, right, which is good because that left some space. But then let us say we have another prompt with this 1 token cat, and then let us say this prompt we predict that this particular prompt will have 2 decoded tokens. So in total there will be 3 tokens, or in total we will need 3 slots, right. Now the problem is, although we might have predicted this decode length exactly for prompt 1 and prompt 2, but as you can see that we just left with 2 slots, right. Now this new prompt need 3 slots. So we cannot actually use these 2 slots. So again that much GPU memory, or those many slots are wasted. So although we could predict the decode length exactly, but still there will be some wastage. There might be some wastage in the slots, because I mean we might have one new prompt which might not fit in the available space, in the remaining space, right. So that means we cannot schedule this new prompt despite having a free memory. So in this case 2 prompt with reserved spaces, we have 2 prompts with reserved spaces, but the prompt grows 1 token, right. So the idea is, the main idea behind to overcome this challenge is, we do not need to pre-allocate this much spaces or this much slots, right. We always know, or we already know that during decoding we generate just 1 token at a time, because again the decoding happens in autoregressive manner, right. So if we already know that during decoding we just need, or we generate one token at a time, that means we also know how the KV cache will grow, how the size of KV cache will grow, right. So we can use that intuition and then dynamically allocate the memory instead of fixed pre-allocation. Okay. So yeah, I mean, in this case the observation is memory needs to grow one token at a time, so that means the reserved memory gets underutilized, correct. So I mean, in this particular case, let's say how was is one prompt we already allocated, we didn't need to allocate all this memory because we already know that we will generate one token at a time. So we just need to allocate one slot, but at the same time if we have another prompt which cannot fit in the remaining amount of memory, we cannot schedule that prompt, right. But we could have scheduled, there is lot of space remaining, correct. And the intuition here is we always know that we just generate one token at a time, so we don't need to pre-allocate all those memory, right. Now we have seen this chunked pre-allocation. The drawbacks, let me summarize the drawbacks. We have discussed that KV cache stored is KV cache needs to be stored in contiguous memory. The static allocation based on maximum request needs result in internal and external fragmentation, and this pre-allocation ignores the fact that memory is needed incrementally and not all at once, right. Again, why it is needed incrementally? Because during decoding we just generate one token at a time, so we need to have space for one more token during the decoding at a time. We don't need the entire space for the decoding, maybe eventually, but not at each step, right. Yeah, we already discussed that internal fragmentation happens due to over provisioning for maximum tokens, and external fragmentation is happening due to memory allocators, right. And due to internal and external fragmentation, we have underutilized reserved space due to all these static allocation policies, right. So with that, let's finish this lecture. In the next one, we will see the main idea behind or main idea to address this challenge of underutilization. Thank you very much.